Wow, there we go. Okay. So welcome to the Climate Resiliency Seminar. There'll be other people that are joining. If you can, make sure you keep your microphone muted. I think the general ground rules, and it's worked pretty well so far, is that I'll do the info. We started recording, and then Mohsen will give our presentation, and then if you've got questions that you think you might forget, you can always put them in the chat, but I think generally it works best to hold all the questions until the end. And I think Mohsen, you'll go through, but he's got about a 45, 50-minute presentation. We'll do, 10 or 15 minutes of questions or until people are satisfied. And then we're going to do a short, what is the infrastructure working group for Wiki been up to, and where are we headed? Just a brief thing kind of following that, which you can stay on for or not stay on for. I will give a short plug. On September 23rd, our own Rob Montgomery will be talking about looking at using climate impacted precipitation and assessing urban stormwater systems. He worked with a master's student from the Nelson Institute for that work. And so I'll send out an advertisement to our listserv and post it in the upcoming seminars in the next day or two, once I get abstracts and other things set, and that'll be up there available as well. The only other thing is I'm going to put, if you, and maybe many of you got here, you saw some of this, I'm going to post it in the chat and I'll do it again at the end. But at that web address, the Climate Resiliency Seminar Series, that's where you'll be able to go to view past seminars. So if you want to share this recording with others, you can do so there, and you can also request your PDH certificate there as well using a Qualtrics survey. It takes me anywhere from a week to a couple of weeks, depending on how busy things are, to get those out to you because I just do them manually and it's just me. So, but you can always harass me, and then that makes me go faster if you need your PDH sooner. All right. With that, I want to welcome you to the talk for today. It's Every Storm Tells a Different Story by Dr. Mohsen Tahmasebi Nasab. And Dr. Mohsen, or Nasab's a water resources engineer and H&H specialist with AECOM. He's out of the Twin Cities. He's done just about, when you think about water, and I was looking at his CV and his awesome personal website and YouTube channel, anything you can think of relating to water, this guy's got it figured out. So I'm really excited that he's here to present today on a topic that I think sometimes goes overlooked, and I know I'm going to incorporate more of this into my hydrology classes going forward, just because it's such a important area in regards to getting the actual implications right at the pipe. So with that, Mohsen, I'm going to turn it over to you.
Awesome. Thank you very much for this kind introduction. It's great to be here today, and thank you for having me. It's a pleasure to be here, and also it's a pleasure to talk about rainfall. Every time that I talk about rainfall and have a discussion about rainfall, different storms, or learn something new truly from the discussion that we have. So, and also the topic, as you mentioned, Austin, the topic of temporal distribution and rainfall is also something that is normally overlooked when we are designing things or planning things, infrastructure. That's a topic that sometimes it's the first step, and we're like, well, let's do this and be done with it, right? And then let's think about more important stuff and designing the infrastructure. But I want to take a different look today, and maybe put an emphasis on this topic. But before doing that, I'm going to give you a short introduction. Maybe let me share my screen over here. All right, I'm sharing. If you don't see my screen, let me know. But right now I am sharing my the cover page of my slides. So my name is Mohsen Nasab. I am with AECOM. I've been with AECOM for about 3 years now as a water resources engineer in the Minneapolis office. Before that, I had a career in academia. I was an assistant professor at the University of St. Thomas. And before that, I was a visiting assistant professor at Bucknell University in Pennsylvania. the area of research, the area of work is mostly hydrology, hydrologic modeling, water resources engineering, and hydraulic modeling. As Austin said, anything related to water, I definitely have the interest to get involved to, and I try to learn more and develop my expertise in different areas as well. One quick fact about me that I have developed the hydrologic model from scratch in Fortran. Some of you might remember that coding language. So that will probably tell you either I'm a very dedicated person or I spend too much in front of computers and with computers. With that, I want to also tell you that many of the visualizations that you see today are created using Python. And I'm going to use this opportunity actually to plug in this course that I have developed about fundamentals of Python for H&H modeling and analysis. It's on my GitHub page. I will share the link with you in the chat. I'm actually showing it right now on the screen. It is not another Python course out there. It is geared towards water resources engineers and H&H modelers. So if you want to recreate some of these figures that I'm showing you today, or if you want to learn more about how you can incorporate Python into your workflows, take a look at this course as well. I'll send the links in the chat later during the presentation. All right, with that, let's get started with the presentation. This is the agenda that I'm hoping to cover today. The presentation is a combination of 3 different presentations that I have given before. I have chosen some material from each and included that into this presentation to be able to show you a wide range of possibilities when it comes to rainfall distributions. I will start with a brief history of rainfall temporal distributions, talk about the NOAA Atlas 14 temporal distributions, how we can incorporate those temporal distributions in hydrologic and hydraulic models, and what are the consequences of that, comparing some of those famous temporal distributions using a hydraulic and hydrologic model. And then I'll introduce stochastic storm transposition and what I see the benefit of that when it comes to design. There's a lot of documents out there that talk about how we can use SST when it comes to planning or flood mapping. I'll try to take a different approach today and talk about how we can use stochastic storm transposition for design specifically. And then at the end, I will talk about some of the takeaways, some of the advantages and disadvantages of what I will introduce today. All right, this is a figure that I usually start my presentations with, and that is from the textbook of Water Resources Engineering from Larry Mays. It's a great textbook. And I love this figure because it tells you the entire process and the workflow of hydrologic modeling, all the way from choosing your rainfall distribution to creating rainfall excess, removing infiltration and other abstractions from it, creating your direct runoff and adding base flow to it to create the full total hydrograph. Now, this is the entire hydrologic modeling process in a nutshell, but today I will be talking about the very, very first step when we are designing something, and that would be choosing the rainfall parameters. And that is what we usually do. We go to Atlas 14 tables, and let's say we choose the 10-year rainfall for this project that you're doing, and then find a temporal distribution, fit it to that depth of rainfall, and that would be the rainfall that we use in our hydrologic model. So today I'll be focusing on this box over here and talking about these processes. Just to make sure, we have different type of civil engineers today, just to make sure that we talk about the same thing. I'm gonna go over the terminology really quick for consistency. So when I talk about temporal distribution of rainfalls, I'm talking about how rainfall is spread over x-axis, which is time. So essentially, what is the intensity of rainfall in different times? There are different shapes for temporal distribution. A rainfall could be front-loaded, which means the intensity of rainfall is higher in the beginning, and as the time goes on, the intensity gets lower and lower. It could be center-loaded. That's the usual bell curve that you have in mind when you think about temporal distribution of rainfall, or it could be backloaded. That means that the rainfall starts smaller and slower, and then the intensity gets higher and higher as the time moves forward. And we call these rainfall hyetographs. Okay, so let's start from the older times that we used to use the SCS 24-hour rainfall distributions for design. And this is not too old because there are areas that still use the SCS curves for design storms. But so this method was originally developed by SCS, which is now NRCS, based on a paper that Kent published in 1973 that had the tables that represented these graphs over here. Different regions in the US represents different type of rainfall. Majority of the continental US falls into type 2. And then you have different other types of rainfall that represents a distribution. So this is the cumulative distribution of rainfall, 24 hours. And on the y-axis, you have fraction of the 24-hour rainfall that has fallen. So by the end of it, this is cumulative, 100% of the rainfall had fallen at the hour 24. This is how you read this. A little bit more insight into that. These different types of rainfalls have been developed for different areas by SCS. For example, type 2 is the one that if you're in Wisconsin or Minnesota or some of the Midwest, Midwest states, you are most familiar with that. It has a sharp peak near the center at hour 12, and it has a very steep rise and steep fall when you think about it. So this is the method that used to be, and still in some places are used as design temporal distribution. But I think it was in 2014 or 2015. Don't quote me on that. I don't recall the exact date, but the NRCS had a essentially document out that specifically mentioned that the one size fit all temporal pattern might not be a good representation of all geographies within these regions that I showed you in the previous slide. And it might underestimate or overestimate the peak flows when you are using the SCS curves. So the next iteration of these SCS curves are the MSE ones. And I'm removing a lot of history just to get to the points that I want to make over here. But now MSE stands for Midwest and Southeast distributions. And I have a map over here for you that shows the state of Wisconsin in a red boundary and shows you different MSE types, color-coded. What you see over here are different counties and different areas are represented throughout Midwest and Southeast are represented using different colors, and each of these colors have different curves that you can use to represent the rainfall, a temporal distribution. Okay, so with that, I want to show you the difference between the type 2 24-hour and the MSE 24-hour as well, just to see the differences that they make. The differences are not a lot. It's a little bit more peaked. The MSE, the red line is a little bit more peaked. One thing that I usually ask people when I present this is how many of you have seen a real storm that looks like this? And very few people in very few cases have seen a real storm that looks like this, right? But this is the design storm that we use for designing the infrastructure. One thing this is another fun fact that I have in my pocket, that more than 50% of the storm falls within 1 hour of these curves. So if you take sometime from 11:30 to about 12:30, more than 50% of the storm falls in that 1 hour. That again tells you that it might not be a very realistic way of representing temporal distribution of storm, but it's definitely based on a statistical analysis of many storms, and that it's a generalized format actually. Okay. The other ones that, the other temporal distributions that came out, I think it was in 2018, these are NOAA Atlas 14 temporal distributions. So if you take a look at those NOAA Atlas 14 volumes that are published for different regions, you can find these temporal distributions in, I think it's in Appendix 5 of each of those volume PDFs. I'm not going to go over all the information over here, but what I want to tell you that now, instead of having only the 24-hour storm, you have 6-hour, 12-hour, 24, all the way to 96-hour durations. These are based on real gauge events that have been statistically classified into different percentages and different quartiles, and I will talk about what they mean essentially in the next slides. They are developed based on the methodology that was developed, that Huff developed. You might be familiar with Huff distribution of rainfall as well. And then the other thing that I want to mention, all of these distributions have been developed for events that are larger than the 2-year frequency threshold in those gauging stations. And again, this is a statistical distribution, so it does not represent a single storm event. It represents an average condition of the storm events for different quartiles. Okay, how do we get to these? That's some of the questions that I get. How do we download these Atlas 14 temporal distributions? When you go to the website that I have included right over here, and I'm hovering over it, you get to select the volume that you want to. For example, volume 8 is these Midwest states. When you click on it, you will have different region options, that which region you want. Minnesota and Wisconsin, for example, are in region 1. You have the option to select the volume. You have the option to select the region and the duration if you want 24 hours, 72 hours, 96 hours, so on and so forth. And when you click to download, it will give you one Excel sheet that you can see the distribution that you have selected. One thing that it's a little bit weird, and I don't know why it's like that in NOAA's website, you can only download one Excel sheet for one region and one duration at a time. If you want to download all of them together, for some reason, you need to do this process repeatedly to be able to download it. So I have developed a very handy tool, and I'm going to click on it and see if I can show it to you. And I'm going to bring it to this screen. So in this tool, you will select and this is online and you can use it. I should have this on my website somewhere, but if not, I'm happy to share this link as well. You will select all the areas that you want to, all the temporal distribution or the durations that you want to, click on download, and then after a while, it connects to the NOAA's website, and it's going to download all of these as CSVs, zip them for the Midwest, and you can click download, and it will download the zip file with all of those Excel sheets. So if you don't want to download them one by one, this is another way of doing it. All right, and this table just shows you what the naming convention for these files are. For example, for volume 8, Midwest states, we have 4 regions, as I showed you, and the naming is based on MW represents Midwest, 1 to 4 represents the area or the region, and the 6 followed by an H represents the duration of temporal distributions that you will download. Again, the links are within the slide if you want to access this information. Okay, so but what do they look like and why they are different from the SCS type and MSE distribution? So when you look at these curves, and I have the example for volume 9, for example, they look like this. They give you different quartiles, and these quartiles represents where is the most of rainfall falls when it rains. For example, for first quartile, the curves tell you that the majority of the rainfall falls between hours 0 to 6, the first quartile. For the second quartile, the majority of the rainfall falls between hour 6 to 12. For the third quartile, from hour 12 to 18, and similarly, for the fourth quartile, the majority of rainfall falls between hour 18 to 24. It is your decision, it's your judgment that which of these quartiles will represent the area better. In addition to that, there are some percentages. Every curve has some percentages represented on top of it. What are these percentages and how should we read them? Let me go to the next slide and give you one example. So I have selected the first quartile, and I'm going to select, this table is from hour 0 all the way to hour 6. And I have essentially this table represents these lines. I'm going to select the 90% curve, and I'm going to select, let's say, these numbers to give you the definition. So let's focus on this hour 6, 35.4. If I want to read this number, the way that NOAA in the guidance document recommends reading that is that in 90% of the cases, and this is the 90, in the 90% of the first quartile cases, and these are the events that have been analyzed by NOAA from different gauges in region, I think this was region 9. 35.4% of the total rainfall fell by hour 6. And now if you want to read, for example, this 1.51, it would be essentially similarly the way that you read it. I have some examples here for you so you can familiarize yourself with how to read it. If you are reading 50%, for example, replace 90% with 50% and this number with this number, and that's the exact same thing that you can read it. To put a little bit more light on how to interpret this, I have one slide. Let's do a very simple assumption. Let's assume that the 35.4% of the total rainfall is 2 inches. So now there are different ways that I can represent that 2 inches. So I'm going to show you 5 different ways in which the same full amount of rainfall, that 2 inches, falls over the 6-hour period. And those are these forms. So I can have a uniform distribution if I have a little bit of rainfall at every time step, and these are the half an hour time steps actually, all the way to hour 6. The summation of these rainfall is 2 inches. I can have a random distribution. Some of them are longer, some of them are shorter. That if you sum all of these rainfall over different time steps, that would be 2 inches. It could be a back-loaded distribution, front-loaded, or a bimodal distribution where you literally have only rainfall in 2 of these half-hour periods and the rest it's 0. And again, the summation of the rainfall for all of these events over a 6-hour is 2 inches. What I'm trying to get at over here is there are different ways of representing 2 inches over time. So it's not just how much rain falls, it also, the timing of it matters because it's going to impact the amount of runoff that is generated, amount of flooding that is generated. And the way that we design the stormwater system infrastructure also depends on the timing of it as well. So if you go to Appendix 5 of NOAA Atlas 14 volumes, you will see that there is some sort of caveat sentence in a single page that tells you that these are there to show you the range of possibilities. And if you're using it, you should be careful which of these quartiles and which of these percentages you're using, because you're going to get very, very different peak flow estimates depending on if you're using them or not. And this is, to me, this means that do not use this for design because your peak flow is going to be very different. That's not what NOAA says. That's my interpretation of this caveat. And then we've been reviewing a lot of design as a program manager for a different state, and we have seen a lot of misuse of NOAA Atlas 14 temporal distributions. And that gave me the idea of let's compare for a real design case, let's compare some of these temporal distributions and see what would be the peak flow for different temporal distributions. So we are going to keep the depth, the volume of rainfall the same, but only changing the temporal distribution and see what the peak flow is going to be and how it's going to impact the design of infrastructure. So in order to do that, the team used HEC HMS 4.12. This is, right now there's a newer version of HMS available. This study is older. We use 4.12, and we use HECRAS 2D 6.5 to design a detention pond, actually. and the inflow and the inlet for that detention pond. We kept every single parameter in the HMS model and the RAS model, the hydrologic model and hydraulic model, the same, except for the way that temporal distribution is represented. So there are two different scenarios, and scenario two has different sub-scenarios. So scenario one, we use a 24-hour MSE distribution, Midwest and Southeast distribution. It's very common. For scenario two, we use NOAA Atlas 14 temporal distributions, but we use different quartiles, Q1, Q2, Q3, and Q4. And we chose the curve that is representative of 90% of the cases. So overall, we have 5 different scenarios that we would like to compare and see how the peak flow changed when we are designing a detention pond. Now, just to give you a little bit of idea, I cannot tell you where this is, but I can show you some of the watershed and some of the things that we considered for the HEC-RAS model and HMS model. This is overall flow pattern. There are 2 different boundary conditions, downstream boundary conditions. This is a highway over here. The water goes under the highway. Some of it goes under the highway to this point. This is the outlet. And then there's another branch. The water goes right over here. It goes all the way down. And this would be another boundary condition. So overall, the water moves from north and northeast all the way to south and southwest. That's the general direction that the water flows. There is a lot of details of modeling, both in HMS and HEC-RAS, that I'm not covering today because that's not the focus of this presentation. For example, when you are doing 2D modeling, you need to refine the mesh to make sure that all the high areas, the roads, are represented well, the channels are represented well, and so on and so forth. So you will end up having from a mesh that is not representative of the topography to a more detailed mesh that represents high and lows of the topography, the roads, the channels, and so on and so forth. And the proposed pond is located right over here. So you can see this is the original topography. There's no pond over here, and there is a pond that we hypothetically put in this area just to see how temporal distributions are going to impact our design. All right, so again, this is the existing condition. This is the channel that I'm actually hovering over. There's no pond over here. And then this is the topography with the proposed pond that you can see on the right-hand side. All right, to give you a little bit more information about the shape of the pond, without going through a lot of details, the pond has an inlet, so the water goes from where my cursor is right now to the inlet of the pond, and cross-section 1 in red shows the cross-section of the pond exaggerated. It's a trapezoidal weir that has the bottom invert elevation of about 12.2, and then the berm elevation is at the elevation of 13. The channel is right over here, and if you take a look at cross-section 2 from left to right, this is the channel, and this is the pond. The pond has the bottom elevation of 5.5 and the side slope of, if I recall correctly, it was 3 to 1. One thing that I want to mention, that usually when you are designing dry bottom detention ponds, the bottom is not flat because you want the pond to be drained. But this is a hypothetical example that we don't care about the bottom of the pond. We care about how water moves into the pond. So that's why the bottom of the pond is not sloped and it's flat. For those of you who are interested in that. Okay, and then the pond has an outlet. You can see it right over here. It's a culvert outlet that takes the water from the pond back to the channel and creates that detention, essentially. All right, so this is the orientation of our hypothetical pond. Now you know the setup, the temporal distribution, the pond. Now let's talk about some of the results. So this animation shows you how the water is moving into the pond over the weir. What I want to show you is the hydrograph that we have simulated at this red cross section. So if you create a red cross section over here and calculate the hydrograph over the 72-hour period, what would be the hydrograph as a result of different temporal distributions that we considered from Q1 all the way to Q4 and the Midwest and Southeast temporal distribution. Remember that the volume, the depth of rainfall was exactly the same for all of these. The only thing that was different was temporal distribution of rainfall. So that temporal distribution of rainfall is going to change the way that is going to change the magnitude and also the timing of the peak. So I'm going to play this animation so you can see how the hydrograph looks like at this red cross section. If I play it, the first one is Q1 90%. It's a bimodal distribution because that temporal distribution has a bimodal distribution as well. The second one is Q2. You can already see the change in magnitude and the change in timing. The third one is, green one, is Q3 90%. Again, change in timing and magnitude. And the fourth one is the Q4 90%. And finally, the MSE, I think it was MSE type 6, is the black one over here. So let me pause over here and just explain this a little bit more. We use different temporal distributions. Different temporal distributions have different assumptions on where the majority of the rainfall falls. And because of that, you're going to get absolutely different hydrographs when it comes to the magnitude, the value of the peak, and also the timing of these hydrographs. Now, how about water surface elevation within the pond and within the channel? Let's talk about that as well. This is the water surface elevation in the pond, and the cross section is this red one. Station 0 is on the right side, and the station 920 is right over here, right after the berm of the channel. So it's from 0 to 920 right over here. You can see when I use MSE distribution, the pond is absolutely full, and this line over here, this is the inlet of the pond, right? And the water surface elevation within the channel is higher than the inlet, which makes sense. This is maximum water surface elevation. That's why water goes into the pond and makes it full. This is what the pond looks like if you are designing it based on the MSE distribution. Now, the same exact pond, what is water surface elevation in the pond and in the channel? I'm going to go to the next slide. Different lines represent different temporal distributions, Q1 to Q4. This is for the 10-year storm. So the light blue one, this one that my cursor is hovering over right now, represents Q1, quartile 1, 90% temporal distribution. The water in the channel doesn't even get to the invert of the pond. And because of that, the pond is not even filled. What you see over here, this blue line over here, is only the local drainage. It's only the rainfall, only the water that goes from other sources, other directions into the pond, not because of the water that is in the channel. Now for Q2, the water in the channel is higher, but still doesn't get to a level to flow into the pond. And again, you can see that light green or whatever color this is that I'm hovering over is again very close to the previous one because the water doesn't get to that point. Now, the only two scenarios that makes the pond full or partially full are Q3 and Q4. For Q3, the dark blue line right over here, the water surface elevation is above the invert of the inlet, and the pond gets filled, but not to its maximum capacity, obviously. You have a very large freeboard over here, so you're not maximizing the use of your detention pond over here. And then the pink line, the one on top, the water surface elevation is the highest, and your pond is very, very close to be over top. So this is the invert. And if you see right over here, this shows the berm right over here where my cursor is. This is the berm of the pond. So if this pink line was a little bit higher, the pond could be overtopped. All right, so far I've been telling you that depending on what temporal distribution you're going to use, you are going to get absolutely different results for the design of the pond that you have. And that's important because we want to be confident when we design something that we are designing something that is based on the characteristic temporal and spatial distributions of the rainfall and the characteristics of the rainfall in that area. Now, Let's talk about the causes of this a little bit in detail, in more details, actually, I should say. So I'm going to go to the next slide. This is the rainfall excess distribution for one sample subbasins in HEC HMS for different temporal distributions, Q1 through Q4. What you see, this orange one, because the peak of the rainfall happens in the first 6 hours, this is the Q1. And the yellow one right over here, the peak of the rainfall happens in the fourth quartile, so that's Q4, okay? Now, as you can see, if I calculate the cumulative rainfall excess depth for each of these rainfalls, the rainfall excess is a different value. You're going to say, wait a second, you told us that you use the same rainfall depth for all of these. How come are these different? What I told you is that I use the same total rainfall depth for all of these distributions. However, when you input a total rainfall depth in your hydrologic model, there's another process called infiltration and loss. And infiltration and loss is going to take some of that rainfall, convert it into depression storage, canopy storage, infiltration, and then whatever is remaining, and that's your rainfall excess that generates runoff, okay, or overland flow. Now, this is really interesting because this is telling me if I have a front-loaded storm, it gives you the highest intensity while the watershed is initially has its greatest ability to absorb, intercept, and store water, right? So infiltration capacity is high. And therefore, when you have a front-loaded storm like this, the losses, including infiltration, depression storage, so on and so forth, is higher in the beginning, and your rainfall is higher in the beginning. So a lot of that storm is going to be converted into different losses. Now, when you have a backloaded storm, similar to Q4, it usually begins with lower intensity rainfall, as you can see on the screen, and then it progressively gets wetter and wetter. And then in the beginning stages, the watershed is going to be satisfied when it comes to initial losses. And then when the larger storm arrives and the rainfall burst arrives later, the initial abstraction may be already satisfied, soil moisture deficit may be reduced, infiltration capacity may be lower, and the depression storage and canopy storage may be already filled. So because of that, a large fraction of the intense rainfall becomes excess precipitation or excess rainfall. I hope I explained this better. So now you understand why you have more rainfall excess, about more than 1 inches than Q1 when you compare Q1 scenario with Q4 scenario. Okay, so now if I want to show you the cumulative rainfall distribution, this is exactly this figure, but instead of showing you incrementally, I'm showing it to you in a cumulative basis. And if I want to put back the numbers over there, you can see that Q4 has the highest cumulative rainfall excess. After that is the MSC 5.72 and all the way to Q1. Okay, for this explanation, I'm hoping that now it is very clear that why we see this kind of scenario over here, the water surface elevation is different. And more importantly, if I play this again and go to the very end, now you understand why the peak of these flows are also different. There are no questions about timing of it because that's obvious. The temporal distributions are different. But now you know why the peaks of these hydrographs are different as well. Okay, going back to this slide, I already showed you the differences right over here. Now, the $1 million question over here that you are asking is, first of all, which of these water surface elevations should I use if I'm designing a detention pond? And then secondly, which one of these rainfall distribution is the correct one? I think you all agree with me that when it comes to the temporal distribution, specifically when we are talking about the statistically derived temporal distributions, there's no correct answer. So nobody can tell you that the MSC is correct, absolutely, or I don't know, the no atlas 14 is correct because of this or that reason. That all depends on where you are, what is the level of risk that you are taking, and many other factors, right? But what I'm trying to do over here from now on is try to give you an alternative option that is up and coming. The computational demand for it is still very high, so you might not see that in design anytime soon. But this is what I think has the potential to be used specifically for some of the design that you are not willing to take a lot of risks. Okay, so in that case, let's talk about a topic that I want to introduce over here. There's no way that I can talk about this topic in full, but I will introduce it in short, and that's the stochastic storm transposition. The first step is to create a storm catalog. And to create the storm catalog, essentially, you are asking yourself a question that, okay, this is a real storm. This is a watershed over here. In this real storm, my watershed is at the edge of the storm. What if my watershed was right over here, where the storm is higher? Or what if my watershed was over here, where the storm is even higher? Or what if my storm was right over there, where the storm is the heaviest, right? So you are going to hypothetically move your watershed to find different values of storm that didn't technically happen in your watershed, but it's plausible. In order to do that, you need two things. You need one is a transposition domain, and the translation of the transposition domain is an area, it's a hypothetical area that you will determine that all the storms that happen in that transposition domain are plausible on top of your watershed as well. That could be a very large area, it could be a very small area, depending where you are in the continental US or around the world. The other thing is, how many storms do we need? Do we need only 10 storms, or do we need 500 storms to create this catalog? And I tried to talk over that briefly. First of all, transposition domain. This is Minnesota watershed. It's a Huck 4. And I'm showing you three different ways that you can draw the transposition domain for that watershed. Again, transposition domain means that the characteristics of the storm that your watershed gets are similar to the storm that the storms that happened in the transposition domain. The purple one is pretty small, and it gets larger and larger. The blue one is very, very large. And these are all plausible transposition domain. This is a very active area of research on how to define your transposition domain. But I'm going to quickly give you one way out of several ways that you can see how your transposition domain is maybe feasible from the meteorological standpoint or not. This is called the pixel level basin envelope coverage comparison. So what it means is, if I pick any pixel of the data, let's say this pixel where my cursor is, and if I extract the value of precipitation, elevation, and dew point for a normal 30-year value, if that specific pixel falls within the minimum and maximum, long-term minimum and maximum of my watershed, if one of those matches that, it's going to be orange. If two of those values, let's say precipitation and elevation, matches that, it's going to be light green. If all three matches that value, the range of minimum and maximum of my watershed, it's going to be dark green. So technically, it's telling you wherever is dark green, the characteristics of precipitation, elevation, and dew point are relatively similar to the characteristics of my lower Minnesota watershed. Okay, so now I have overlaid the transposition domain on top of this, so you can judge which one you are going to go with when you are choosing your transposition domain. Unfortunately, it's not that easy. If it was that easy, that would have been great, but it's not like that, because you also need to have in mind that you will need a long history of rainfall. So the larger this transposition domain is, the chances that you get many storm catalog items is higher. Let me show you what I mean. So let's assume that our transposition domain is the purple one. Now, I'm going to move my watershed. The watershed, the original location is in black. The pink dashed line is where I hypothetically move the watershed, the centroid of the watershed, to get the rainfall. And I have ranked all the rainfall from the highest one, which is this one. So if I move my centroid of the watershed to this point, it's going to capture the storm that did not happen on top of my watershed, but happened a little bit to the west. If that happened, that's a hypothetical scenario. If that plausible storm happened, the average rainfall over lower Minnesota would have been 5.24. Now, I have done this many, many times to figure out what are those areas that give me those rainfalls, and I have ranked them. So if I play this animation, you'll see the watershed is moving in different directions. And as it moves, you can see that I have ranked all of these average basin precipitation from the highest rank all the way to the lowest rank. So because this transposition domain is relatively smaller, I'm not going to get thousands of storms over here. I'm going to get only hundreds of storms. So I'm not going to play this animation, all of it, but I'm going to go all the way to the end of it to show you that I only get 228 plausible storms over this area. Now, what if I choose the larger one, the red one? This larger one has a larger area, so the chances for me to get larger storms and many more storms is higher. So again, the same thing. If you start moving your watershed across time and space, these are the this is the time and the space. You can see it over here. This time, I'm getting about 500 storms, so about 300 storms more, and that's good. I want more storms. So sometimes, even though your transposition domain might not be exactly representative of your watershed, you're good with it because you're going to get more storms. Now, there are challenges with that. The original watershed right over here does not receive any tropical storms, but the transposition domain, you can see that there are some tropical storm remnants that cross over that. In order to have a better representation of the storm, you need to go and check these tropical storm remnants. If they are not representative in your watershed, you need to manually remove them from the catalog. So the storm's temporal and spatial distributions are more representative of what can really happen on top of your watershed. Okay, with that, let's say that you have 500 storms, and this shows you different temporal distribution of those 500 storms, just 100 of them. The green one is the one that is highlighted. All the gray ones are all the other ones. I just chose 100 of them because I don't want to make this a very busy graph. But you can see every storm is different. Every storm is telling you a different story over here when it comes to temporal distribution. And the y-axis is the normalized rainfall intensity. So I have divided every single storm by its peak. That's why you have the value of 1 on the top of your y-axis. Now, once you have all of these storms, the stochastic transposition process occurs in your H&H model. You're going to run the storms over your watershed hundreds and thousands of times. You can optionally have a stochastic representation of antecedent moisture condition. Infiltration parameters can be changed, or even matting roughness can be changed. And that will give you millions of runs, right? So when you have these millions of runs for your H&H models, then the result would be that instead of having one deterministic value for your water surface elevation and your peak flow, you have a probabilistic output of your water surface elevation in the pond and peak flow in the pond. This will allow you to answer important questions that you cannot answer deterministically. For example, it allows you to answer the question of what is the probability of overtopping based on this million simulations that I ran for different plausible storms? Or even better, what fraction of simulations exceeded the pond crest actually? Or questions related to overtopping. The other type of questions that you can answer is related to water surface elevation. What water surface elevation is exceeded in 10%, 1%, and 0.2%, or another selected percentage of simulation. This helps you to understand the level of risk And it helps you to understand when you're designing what is the level of the risk that you are willing to take. If this pond, for example, is in a very populated area and you are not willing to take a great deal of risk, then you need to justify your design based on that. The other type of question is how often does the pond remain below 25% or so its usable storage? So in other words, is this pond is getting used or not from different simulations? Is it just getting used once or twice every 10 years? Or is it going to be used more than that? Or questions along that line. And eventually, what is the probability of achieving the emergency spillway? So again, the shift here is from the deterministic way of designing that you have one number for your design and you're going to report that one number and that would be it, to looking at it from a more probabilistic view of it, and informing the client that the level of the risk that you can design for. And the client is the one who is going to, of course, with your advice, is going to decide what is the level of risk that is acceptable in this area that I'm going to design for. Now, the question is, do we need to do this process for every single design? Of course, no. If you're designing a BMP, for example, a rain garden in a city, this is an overkill. This is usually for the infrastructure that you see at least some level of risk associated with it that you want to go through this process. I'm not going to go through all of these benefits of stochastic hydrology over deterministic approaches because there are challenges as well. It's not all. But one thing that I want to highlight that this method, this SST, a stochastic hydrology, captures the natural variability. So essentially, if you consider aleatory uncertainty as random uncertainty, this is good at capturing the random positioning of storms, both spatially and temporally. Okay. The other thing is that this is not based on any statistical distribution. These are real storms that have happened. You're just running them over and over, right? But before talking about the first 3 bullet points, I'm going to talk about some of the challenges. This is very computationally heavy. It's getting better and better because we are getting access to better computers and cloud computing. But still, this is computationally heavy, and setting up the model is very complex. The other thing that I want to highlight, it still doesn't solve the epistemic uncertainty, the knowledge gap that we have. We are bound to the level that our hydrologic and hydraulic models can represent the reality, the physical reality. This process is not going to solve that. We still need, if you want better representation of the reality, you want better physical models. This is not going to solve that problem. All right. I just realized that I really talked today, huh? So I'm going to pause over here. That's my last slide. I'm going to open it up to question and absolutely discussion. I would love to hear your take on deterministic versus stochastic and probabilistic design and your thoughts on this. All right, thanks, Austin. Open. I haven't checked the chats if there are any questions, but if there are any, I'll be happy to answer those as well. I'm going to send the links that I promised to you in the chat as well, in case anybody is interested in that Python course or anything else in my, website and the GitHub.
So I've got one question. This is excellent for data that we have, and obviously maybe that, and this is a climate resilience, not a climate change, but let's say we want to talk about the climate. I mean, for climate resiliency, being able to mine a catalog of storms and chop down on some of that uncertainty and picking a distribution. I mean, this is the way, right? This is a great way to do it. Is there efforts, or are you working with others in terms of going and getting data out of either downscaled output or dynamical models and looking at how those things change and how it changes the temporal distribution, what that means if we're looking at 2050?
Yeah, that's a great point and a great question, and very fitting of the time that we are living right now. So the beauty of this looking at things probabilistically and temporal distribution is that these temporal distributions, we can disassociate them with their exact overall depth by normalizing them. So technically, we can have hundreds and thousands of different temporal distributions over an area without even looking at what was the overall depth because they're normalized. Now, if we have the climate data from the climate models, or I know Atlas 15 is going to come out soon, we do have those depths that are climate aware. Now, let's assume that we have those depths. If you multiply those depths to this template, to this temporal distribution, you have even a more powerful climate aware system that can simulate the risk and the probability of how your infrastructure is going to react in future based on the climate rainfall depth and temporal distributions that are common in that area. Does that make sense? Did I answer the question?
Yeah, thank you.
Any other questions, comments? And don't jump in altogether.
This is Rob Montgomery. Unfortunately, I came in late, but boy, this was a great talk. Thank you. I have the grumpy municipal engineer question. Okay, so the prescribed standards typically are, we only use one distribution and we make you assume a curve number or something, whatever the rainfall runoff transformation is to be reasonably conservative. And we prescribe that you do things in a conservative way in terms of computing runoff. And you come in with this sophisticated approach, and there's a lot to learn here. Mm-hmm. What has been your typical response?
Oh, that's a great question, Rob, and a great comment. And it's dangerous too because I can talk about this for hours, but I'll keep it short. So as I think I alluded to it briefly, but let me expand on it a little bit more. There is no way that we can replicate this process that I showed you for every single design that a state, a city is doing at all. Not just because it's complicated and the learning curve is very steep, because it's not needed. There are many cases that the level of risk that we are dealing with is actually small enough that we are comfortable with the conservative assumptions that are prescribed by local agencies, government agencies, that we can keep using that and be fine with that. But when it comes to infrastructure that is going to be used, that is going to be very important, high risk for a very long time, and we care about the failure or not failure of that infrastructure, this is an approach that gives us a wide range of, that gives us answers to a wide range of our questions. And it's very common for folks to ask, okay, what happens if this scenario happens? What is the chance of overtopping this? What I envision, and again, I'm seeing that more and more communities are moving towards the probabilistic analysis, and even bigger agencies are moving toward probabilistic analysis. But I still see the value, and I still understand, and I still believe that the conservative assumptions that we are making with the deterministic approach is going to remain in place for a good majority of the design that we are doing on an everyday basis. And there will be some cases that we're going to go all in and we're going to do a full probabilistic analysis because we think this infrastructure is important enough that it deserves this kind of scrutiny into it. As far as learning curves and the computational power needed, I think the speed of development is so fast that it's just mind-boggling how we are learning to do these things. Right now, the SSC process is incorporated in HMS 4.13. So if you want to run it on your computer, you can. It's going to take a very long time, but you can do it. And with the dedicated GPUs in the new computers and with the better combination of CPU, GPU computing, I don't see that they vary far, that we can run a full set of stochastic hydrology on a normal laptop that I have that takes only, I don't know, 3 hours to run. And that's very doable. And I'm excited for that day to come eventually, because for the bigger transposition domain for lower Minnesota, it took me about 3 weeks to run that scenario on a workstation. So it is time intensive, and you need good computers to be able to do that as well. I know I tried to answer your question, Rob, and I went ahead and answered a couple of other, or talk about a couple of other things as well. I hope this was something that you were looking for, and I at least touched on some of the stuff that you mentioned.
The very, very interesting response. You did get another question.
Absolutely.
I think it's in the chat.
Oh, in the chat. Okay. What radar product do you use when running on SST analysis? We need the analysis that I showed you is based on NOAA's AORC analysis of the record for calibration. And that data is 1 kilometer by 1 kilometer grids. And it's available from 1979 all the way to 2026. So a long period of rainfall available for the United States, which is amazing. It's a great data to have. The quality of it, though, and how you can find some of the artifacts, radar artifacts, satellite artifacts in that data, that would be another actually good topic for a presentation. But it's fascinating. Yeah, absolutely. Awesome. And I want to offer, if anybody has any questions later when you are thinking, I know this presentation was so memorable that you're going to all think about it. If that happened, and if you have any questions, feel free to reach out to me. You have my email address and website and everything. Reach out to me. I'm the person who likes to talk about rainfall and water resources, so reach out to me.
I'm going to stop recording really fast.